You may have heard that you can't trust atoms because they make up everything. But what exactly is an atom, and why are they so critical for understanding matter and therefore chemistry? Here I'll be introducing the atom and even smaller subatomic particles that form the atoms. Watching this video is one step towards meeting the learning objective of being able to describe the structure of atoms. Atoms provide the essential connection of macroscopic properties that we can see to the fundamental composition of the material. They are the basic component of all ordinary matter. In chemistry, the word microscopic is often applied to the atomic level details, even though we can't see the atoms themselves because they're too small with standard microscopes. The image on this slide actually shows iron atoms in a ring that was taken using a scanning tunneling microscope, or STM, which is a specialized instrument that allows us to see this level of detail. Atoms are the smallest identifiable unit of an element, and there are 91 naturally occurring elements, as well as over 20 synthetic elements. You will learn a lot more about atoms and their interactions throughout this course. Atoms contain a small positively charged nucleus, which contains positive protons and neutral neutrons, and this is surrounded by a cloud of negatively charged electrons. This is our modern picture of the atom, and we will talk about how we know this over the next few minutes. You may see other representations of atoms where electrons are shown as moving particles. We will talk more about the specifics of electrons in later videos, but for now just be aware that these images are attempting to represent the same idea as the previous image, where we have a small nucleus surrounded by a large cloud of electrons. Atomic theory is the scientific theory that all matter is made up of indestructible particles. There are three important laws that led to the development and acceptance of atomic theory. These are the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. We will now look at each of these laws in more detail. First, we have the law of conservation of mass. This scientific law results from observations that show that matter is never created or destroyed in chemical reactions. This means that the total mass of a chemical reaction never changes, it is only rearranged. This idea is consistent with matter being formed of small indestructible particles. In a chemical reaction, the combined mass of the reactants is always equal to the combined mass of the product. In the example shown here, 7.7 grams of sodium and 11.9 grams of chlorine are combined, and this is a total of 19.6 grams, to make 19.6 grams of sodium chloride, or NaCl. Next, we have the law of definite proportions, which is that for all samples of a given compound, we have the same proportions of their constituent elements. That means that if you have 18 grams of water, there will always be 16 grams of oxygen and 2 grams of hydrogen, resulting in an oxygen to hydrogen mass ratio of 8, or 8 to 1. Another way of thinking about this law is that atoms always occur in definite whole number ratios. So there are always 2 hydrogens for every 1 oxygen in water. It doesn't matter if your water sample comes from a lake or an iceberg or even your bathtub. Finally, we have the law of multiple proportions. This law states that when 2 elements form different compounds, the ratio of masses can always be expressed as a small whole number ratio. Thus, if we consider CO and CO2, we can determine the mass ratios, which for CO is 16 to 12 for the mass of oxygen to carbon, and carbon dioxide is 32 to 12 for the mass of oxygen to carbon. We can reduce those numbers by dividing by 12, and we get 1.33 to 1 for carbon monoxide and 2.67 to 1 for carbon dioxide. If we take the ratio of those two numbers, we get a small whole number ratio. This is the illustration of the law of multiple proportions. The idea of an atom has actually been around for a very long time. The earliest recorded ideas were found in ancient Greek writings. These were generally vague and proposed many types of atoms that moved randomly through empty space. We will now look at some of the key developments of modern atomic theory, including the discovery of the subatomic particles. First of all, in 1803, Dalton proposed the core of modern atomic theory. His premises were that each element is composed of atoms, which are tiny indestructible particles. All atoms of a given element have the same mass and properties, and that distinguishes them from atoms of other elements. Atoms combine in whole number ratios to form compounds. And finally, atoms of one element cannot change into atoms of another element. They only change the way they bind to and interact with other atoms. A bit later, about 100 years, Thomson determined that all atoms had particles containing negative charge through experiments with cathode ray tubes. The particles in these rays were later termed electrons. Through these experiments, the mass-to-charge ratio of the electron was determined to be negative 1.76 times 10 to the 8th coulomb per gram, and shortly after, the charge of a single electron was determined by Millikan using an oil drop experiment. These cathode ray experiments demonstrated that all atoms indeed have negative particles, or electrons, associated with them. Thomson also proposed that the negative and positive charges in neutral atoms were evenly distributed throughout the atom. The next key discovery was by Rutherford, who was attempting to verify Thomson's model using an experiment where positively charged alpha particles were aimed at a thin gold foil and then detected in all directions. If the Thomson model were correct, the alpha particles should have been observed to pass straight through the gold atoms, but instead, Rutherford actually observed that the particles were occasionally deflected in all directions. This led Rutherford to propose that atoms actually had tiny positively charged nuclei. When the positive alpha particles interact with the positive nucleus, they are deflected. This is the foundation of nuclear theory, where most of the atom's mass and all positive charge are contained in a small core called the nucleus. Most of the atom's volume is actually empty space with tiny negatively charged electrons. And there are equal numbers of negatively charged electrons and positively charged protons so that the atom is overall neutral. Later work by Bohr, Schrödinger, and others led to a better understanding of the paths of electrons. We will revisit the motion of electrons and how they behave later in this course. Finally, although the Rutherford model was highly successful, it was found to be incomplete because it didn't account for all the mass of the atoms. Later work in 1932 showed that the remaining mass was due to neutrons, which are neutral particles within the nucleus. Here is a summary of the subatomic particles which make up all atoms. You can see that protons and neutrons have a similar mass, while electrons are much smaller. Protons and electrons have opposite but equal charges, and neutrons have no charge. Now you have been introduced to the atom and the three subatomic particles that form it. Thanks for watching.